In this video, I'll be showing you how I folded these two shapes from my Pythagorean theorem proof video, and show you the calculations that I used to ensure that they're exactly the same size. If you haven't already, you can go back and watch that video first, otherwise let's jump right into it. When I created these models, I actually started with this shape here, and then folded the other one to match it. It took me a while to find out a good way to fold this shape. I actually came to it by looking at some diagrams for making origami picture frames. Here's how this was done. I've created a diagram here that highlights some of the main features. Basically what we do is we pick a point along the side of the square, and then mark points that are the same distance along each of the four sides. If we fold the corners in along the lines defined by these points, then we get another smaller square here. Folding the corners of that smaller square backward again into the center gives us the desired shape. There's colored triangles on the outside and the white square on the inside, just like what we have here. Notice that we can't just pick any point along the side of the square to do this. If we had started with this point further to the left, the triangles in the center wouldn't actually touch each other. On the other hand, if we moved this point further to the right, the triangles would kind of overlap with each other, and the square in the middle wouldn't touch the edge. I wanted to find out where to place these points so that the white square's corners exactly touched the edge of the final figure. In other words, I needed to determine the ratio of this line segment, x, to the side length of the square. When I was first trying to work this out, I made a couple test pieces to see if I could figure out the correct ratio just kind of by accident. I was hoping it'd be a tidy, elegant solution. That way it'd be really easy to fold. So here's my first two attempts. On this one, I set x to be 3/4 of the square side length, and on this one, I set it to be 2/3. Now you notice, like I said before, on this one, the triangles don't actually touch each other, and on this one, the white square doesn't go all the way to the corners. So neither one works, but conveniently, we found an upper and lower bound, giving us a bit more direction regarding how to proceed finding that ratio. Now there are several ways to do this, but my favorite way to calculate the ratio involves a creative use of an infrequently used trig identity. Let's inspect the diagram. First, notice that this diagram is full of similar triangles. The one I'm most interested in is this triangle here. Now I'm not going to go into the details of showing how I know that all the angles are the same. I'll leave this one up to you folks to do in the comments. But the key point is I'm going to try to find the angle of this here, which I'll label alpha. To do that, I'll be taking advantage of the fact that this is an isosceles right triangle. I've reproduced that main part of that diagram here. So let's start by defining this segment as 1, and we'll define this piece here to be equal to some length a. We know that this must also be equal to a, so we can write the following expression. We can write tangent of alpha is equal to a over 1 plus a. Here's where we're going to bring in that trig identity. Some of you may be familiar with this. It's the half angle identity for the tangent function. We have tangent theta over 2 is equal to sine theta over 1 plus cosine theta. These two expressions look awfully similar. In fact, we just need to determine where sine theta equals cosine theta. Let's do that quickly on the side here. sine theta equals cosine theta. Divide both sides by cosine theta to get sine theta over cosine theta equals 1. This is of course the same as tangent theta equals 1, and since we know we're working with an acute angle, theta is equal to pi over 4, or 45 degrees. So there we have it. We have our solution. Alpha must be equal to pi over 4 over 2, or more simply, pi over 8 radians. We can use this identity again to find the ratio of x to the side length of the square. If we take the square to be of unit size, then we can write the following expression. X equals 1 plus cosine pi over 4 all over 1 plus cosine pi over 4 plus sine of pi over 4. Let's simplify a little bit. Both cosine of pi over 4 and sine of pi over 4 are equal to 1 over root 2. So let's replace those. Let's tidy this up a bit. Let's simplify, put everything over a common denominator. And we can start doing some canceling out. Now this may not look like the most attractive solution here, but not to worry, we can simplify it a little bit more just by multiplying the numerator and the denominator by root 2 over 2. Oh, sorry, root 2 minus 2. And once we multiply everything and cancel everything out, we're left with negative root 2 over negative 2, or more simply, 1 over root 2. Well, this is great. This is consistent with our experimental upper and lower bound. It's in between 3/4 and 2/3. And as an added bonus, it's really quite easy to fold. So let's do that now. We'll start with a piece of paper, color side down. And in order to construct a segment of length 1 over root 2, what we can do is first take a segment of root 2 and just split it in half. So let's fold both diagonals. And these are going to serve as guidelines. Next, we'll fold the edge of the square to match the center diagonals. And we'll do that all the way around the square. Now remember, we want segments of length root 2 over 2, or half of root 2. So we just need to make a mark where this line segment here falls on the edge of the square. Probably the easiest way to do that is just to fold these back in, and then fold along the diagonal. Make a sharp crease right here. And then when we unfold, you'll notice we've created two congruent triangles, and we've marked off that point 1 over root 2 from here, and we'll just do that again for each side of the square. So now that we've got our guide points here in the 4 sides of the square, we can just fold those triangles in. And to finish it off, we'll fold the corners back. And there we have it. I rushed through this one a little bit, so the corners aren't all perfect, but if you take the time to go and make those folds carefully, you should be able to get a square that fits perfectly on the corners of this circle. And there we have it. Now we'll just have to fold our other shape to match this one. The first few steps are actually the same, so we'll just unfold this one to show you. What we want to do is first create a square in one corner, then make the second square, and then tuck all the extra bits we don't want into the back. We can kind of see the outline of the triangles that we want. For example, right here. And so we'll just use this line segment to show us how far we need to fold in on one of the sides to make our first square. So right here in the corner, I've created that first smaller square. What I'll do is just fold this corner back. And then bring these pieces forward in the front. That way we get these colored rectangles, and we can just flip this over to the front. for that solid square. And to make our second square, we can use this line as reference and just kind of measure that out along here. So there you can see the outline of our second square. And we'll use the same trick as before. We'll just fold these back and tuck them out of the way. And there you have it. There's the finished second figure. Like I did with my original figures, you can always check that they're the right size by overlapping them a little bit. And if the triangles match up, then you did it right. Thanks for watching this video. If you wanted to go back and take a look at the original, I've included a link over here. And of course, don't forget to like, comment, and subscribe, and I'll see you next time for more foldable math.